Hello, my name is Matthew Temple and I've just started at UDP in Santiago. Today I'm going to be presenting some of the key highlights from this paper which I recently posted to the archive. So this talk is going to be about emission from sublimation temperature dust in quasars. So it's known that quasars and indeed other AGN show emission across a wide range of wavelengths corresponding to dust at a wide range of temperatures. But today I'm going to be focusing from emission from the hottest dust, which is located closest into the accretion disk, where the temperature is set by sublimation to be around 1200 to 1500 Kelvin. And the emission from this dust peaks around 1 to 3 microns, and indeed dominates the emission in the 1 to 3 micron rest frame wavelength range. At redshifts of 2 or so, this corresponds to the WISE W2 passband, which I'm plotting here. So for reference, this is a quasar SED at redshift 2, where you can see H alpha. The black dashed line is a 1280 Kelvin black body, which is what we see the dust temperature to be consistent with. And then you've got the UGRIZ passbands from Sloan, YJHK from UKIDS, and W1, W2 from WISE. And today I'm going to be comparing the dust emission with the properties of the rest frame UV emission lines, and in particular carbon-4. Carbon-4 is a high ionization line which is located at 1550 angstroms. And this line often shows evidence for outflows through skewed asymmetric emission, with an excess of emission in the blue wing, which is believed to be due to material outflowing along the line of sight towards the observer. So throughout this talk, I'm going to talk about carbon-4 blue shift, and that's the Doppler shift of the median line flux, which is a measure of the strength of emission from the outflowing component. So objects with larger blue shifts show more skewed emission, which is moving faster towards the observer. So I construct a sample of around 5,000 quasars, where we've got data from for photometric data from SJSS, UKIDS, and WISE, covering the rest frame sort of 1000 angstroms through to 3 micron range. And I've got spectroscopic coverage of the carbon-4. And what I do is I fit a model SED to the photometric data, where the main free parameter is the strength of the hot dust component, which I model with a black body. And the strength of this component I'm going to refer to by looking at the normalization of the hot dust black body relative to the power law continuum at 2 microns. So in effect, it's a measure of the covering fraction of hot dust. It's the ratio of luminosities between the hot dust black body and the quasar continuum. And this is what I'm plotting on the y-axis here. So objects at the top here have got stronger emission from hot dust. Objects at the bottom have got weaker emission from hot dust. And on the x-axis, I'm showing the blue shift of the carbon-4 emission line. The objects on the left with 0 blue shift show symmetric emission at the rest frame lab wavelength. Objects with large blue shifts show asymmetric emission, which has been Doppler shifted to the blue, so showing stronger evidence for outflows. And you can see there's this clear trend. Objects with stronger hot dust emission also tend to show stronger evidence for outflows in the UV emission line profiles. But it's known that the emission from carbon-4 is strongly correlated with things like the Eddington traction. And so it's reasonable to ask whether the other things might be driving the correlation with the hot dust properties. So here on the x-axis again, I'm plotting the carbon-4 blue shift. On the y-axis, I'm plotting the UV luminosity and also the Eddington ratio. And then for each hexagonal bin in this space, I'm plotting the median hot dust strength, whereas as before, I'm using the ratio of the hot dust luminosity to the quasar luminosity at 2 microns. And I'm only plotting bins with 5 or more objects. So bins that are coloured red show stronger hot dust emission on average. Bins that are coloured blue show weaker hot dust emission. And we can see that at fixed carbon-4 blue shift, there's very little trend in the hot dust emission as a function of either the luminosity or the Eddington fraction. However, at fixed Eddington ratio or at fixed luminosity, as we move left to right, we recover the trend with objects with stronger carbon-4 blue shifts having stronger hot dust emission. And so this is telling us that whatever's driving the correlation between carbon-4 and the hot dust strength is not the Eddington fraction directly or the luminosity directly, or indeed the black hole mass, where we see very similar results. So if you've got any further questions, please do have a look at the paper and feel free to email me. Thank you.